Thank you very much, Ed. And to all of our speakers. We're now going to open up, we've got time for questions, Q&A from the audience, from online, and I'm going to start with one question for myself while you guys come up with your questions. Your questions can either be to an individual panelist or to the entire panel. So I'm going to ask the entire panel, if you were, is there one particular physiological process that you don't currently have in your model that you would like to? You think you'd be able to advance the science if you were able to layer in another physiological feature? So,
an immune system.
You're going to like my answer, Lauren. Transport, because it may be there, but we haven't really characterized it.
So I guess, Jed, do your cells, they will form like the full monolayers? Like, can you like almost kind of make like a the normal hepatocyte cords?
They do, yeah. But we haven't really looked at functionally at transport. Some of the transporters are expressed, it looks like, but we need to do functional assays.
I think immune cells are the missing, even though I had one type, but they're more needed.
Yeah, and you've done some stuff with neutrophils as well to model disease.
Yeah.
Also, wonderful. Misba?
I would add on immune cells, macrophages, everything, because right now in my organoid model, we just have epithelial cell population. So we need those cells and microorganisms and that, everything, so probably.
You bring up a good point. Ed and I had talked about this earlier. We're microorganisms, right? So especially when we think about the microbiome, both of the intestine and of the milk, I think that's another factor that we still haven't considered in trying to truly recapitulate some of the physiology that we have in these systems. I think the other thing too to think about, even as a group, as we look at all of these different NAMs, we've heard a lot today about changes in maternal disposition of chemicals or drugs. And then when we go and look at just a specific organ, whether we're looking at just the placenta or just this part, I think also ways that we might be able to link some of these systems to especially think about changes in maternal hepatic metabolism that can then change across gestation, which could also impact the relative profile of metabolites or chemicals that the placenta will see or that the fetus will see as well. So I think that's another layer that we have to continue to consider.
Yeah, it's a really great point. I think, it's metabolism and transport too is so upregulated during pregnancy, right? And I don't know. Yeah, exactly.
Some are up, some are down.
It's differential, right? So, but that's an excellent point. I don't know if it's accounted for really in these model systems.
Wonderful. Open it up to the audience. Yes, please.
Hi, thanks so much for all panelists for the impressive talk. I have a specific questions to Dr. Lampe because I think your data is very impressive, and I'm also applied PBPK for.
Are you an NIH reviewer? Can you serve on the panel?
No, actually, I'm Tomoyuki Mizuno from Cincinnati Children's, and I also applied PBPK model for the pediatrics and the neonate infants. That's why I'm also interested in both metabolic enzymes and transporter functions in the neonates. So my question is, because you used iPSC-based hepatocyte, and we learned that each different cell systems have strengths and limitations from the monocyte to monolayers to the 3D organoids and also the organ on chip. So I'm curious about your opinions. Do you think that your hepatocyte system is suitable for characterizing neonate metabolism, or you are also exploring some organoids or organ on chip systems?
Yeah, great question. As I was saying, it's all models are bad, some are useful. I think this model is useful right now for drugs that were primarily metabolized through the 3A pathway, right? Because that's going to be 3A7. That's what we were going for. It's not optimal for drug metabolism in general, at least not what I would like to see. If I were to say it was a really good model that really recapitulates fetal/neonatal drug metabolism, I don't think we're there yet. Transport, we need to look at immune system cells. I mean, if you're going to go, absolutely, that's where we want to go, right? To organoids, more complex systems. And then you're going to have to add in other cells. And, people are trying to do that, but sometimes they forget that, those other cells represent that fetal/neonatal phenotype too, right? If you're going to put in Kupffer cells or whatever to model your neonatal liver. So it becomes an order of magnitude more complex when you go to organoids and organs on a chip. But I do appreciate the question. That's where we'd like to go ultimately. Yeah.
Sounds great. Thank you. And I also agreed with you that this is an all-moving target. And the function is dramatically changes over time during the course. So I'm curious if you can identify the developmental stage of your hepatocyte system, because that's also significant. Impact
great question. Yeah, exactly. It's a moving target. So where are we on that target? We think we're somewhere between late fetal, early neonatal stage. So like less than a week old, probably. But somewhere in there. It depends on what gene you're looking at, honestly. But great question. Yeah.
Thank you.
And I would like to add on, I would like to quote Dr. Menon, as he said in the morning, like no model is perfect. So basically you have to ask what you want to study, and accordingly you can choose the model of your work.
Yeah, I'll just tack on with that. Again, I think it's really important, the functionality aspect of it, right? So when I went into this so naively thinking that at the end of the day, we're going to get a cell that's going to look exactly like a neonatal hepatocyte, right? I just had no appreciation how complex it is and difficult to get that. And you adjust one growth factor and then you increase CYP3A7, but you decrease UGT1A1, you know? And so it's really, really tricky. So the functional aspect's really important.
Next question, please.
I have a question. Lars Bode, UC San Diego Human Milk Institute. I have a question about the mammary gland. Mammary gland changes quite a bit during lactation. So colostrum, we heard, is different than mature milk, but it really changes from day to day almost. So in your model, do you see that in addition to the lipids that you express there, do you see alpha-lactalbumin? Do you see lactose being expressed? Do you envision that that changes transport expression as well?
Okay, thank you for the question. It's a great question. We want to do that, but as of now, we have not done it. Like in our future, we will try to explore, as I already mentioned, there are different stages for milk production as well, and that is how mammary gland physiology changes. But since we are very restricted, especially in case of cellular models for studying lactation, so we have not gone there yet, but probably maybe in future, we'll explore that option. Thank you for the question.
And then if I may, another question for the intestine as well. Do you see a lot of mucin expression in your models as well? And do you envision that a thick mucin layer might change transport activities, molecules maybe not even reaching transporters? Is that something you're taking into consideration as well?
That's an interesting question. We do see some expression, but I was actually just at the Society of Toxicology meeting a couple of weeks ago, and one of the things that other folks are doing, we've been talking about wanting to do, is you take that transwell system and then you essentially, in the apical layer, you withdraw the media to get an air-liquid interface, and then they get even further differentiation. So I'm sure when you do that, the mucin expression is going to go up significantly as well.
Thank you.
So I think one other question that always comes up when we're trying to develop these new approaches and methods is trying to determine susceptible populations, trying to capture the inherent variability and heterogeneity within populations. And I'm curious if you guys have given some thoughts. I know Ed showed a little bit about some of the different donors, and Pouria kind of talked about using a donor matched for all of the different endpoints, both between the explants and the tissue chips. But how do we start to identify, and especially if we're thinking about it often with like a risk or toxicity lens?
Yeah, I think that's a really great point. You know, if you just look at 3A7, there's a lot of inter-individual variability in terms of expression. And that's even within the same ethnic group, right? And then you start thinking about different ethnic groups, maybe you have some 3A5 expression going on, and it gets, again, an order of magnitude more complicated. But I do think, so that's the gray cloud, right? But the silver lining is, I think with all of these methodologies, we have the power to tweak them enough, right? Through, you know, new like CRISPR-Cas9, things like that, where you can introduce a gene like 3A5. You wanted to look at what the effect that would have. So we can tweak them to represent these different individual phenotypes, right? Where you might see different levels of metabolism or transport. But very good point.
Yeah, I would say, Lauren, for special populations, access to tissue is going to be a major challenge, because people with primary cells, excuse me, as opposed to you can do the genetic editing if you're looking at rare conditions, and then you can do that. But then you come back to the question of you can do the editing of a parent cell line of iPSCs and compare it to the edited rare disease, but then you've got the caveat of you're back to the fetal phenotype.
I like the fetal phenotype.
So in our case, so we were lucky. So we started with some cell lines and some primary cells. But when we get to the amnion foundation, that's where I actually started to appreciate, like, if there is a place that you can get a donor cells. So that's where the true power of these NAMs or the new technology will start to show up, because not only we used cells that are donor specific and we have all the information from that specific, and then now in the next line of donors we can compare them. So all the genetics, the sex differences. Then we had this opportunity again, like these are the experiences that I learned from this study, that we went back to the source and asked them for the explant. So now we have the amazing sets of data from a same donor that we can identify the changes in terms of toxicity. So it's again, it comes from the donor. It's hard to achieve, so it was a unique situation, and I'm very proud of that collaboration between us and Amnion Foundation. But that's one of the solutions, and the NAMS technology is just a technology that provides a fasting process in order to get to the point.
Yes, please. Question.
Hi, this is Zhen Tao from Eli Lilly. I just have I'm very fascinated about these novel methodologies, but I just have a general or maybe naive question. Like, are these novel methodologies, whether it's iPSC-derived cells or like organ-on-a-chip, is the in vivo correlation better than the conventional or like transporter or metabolism studies, or like how is the translatability, how predictive of this all new tools or models that we're developing right now?
You took my next question.
Yeah, it's an interesting question, and I think it's three words been brought up multiple times today. It's about the context of use. So for the proper context of use, a NAM can be a very powerful tool, but you can't always ask the tool to answer the question that it's not made for. And so it's really a matter of, what is your NAM capable of doing? So for example, if we're interested in, say, inflammatory bowel disease, right now our intestinal NAM is immune system free. So it's not a good NAM for studying IBD. So it's really all about defining your context of use. And it is something we're dealing with the iSTAN program for our kidney NAM. And we're defining what is the context of use. In other words, what can we do with it? But just as importantly, what is it not capable of?
Yeah, I think that's a good point. All of them come with caveats, right? None of these models are, independently perfect or even as good as the gold standard, whatever that is. So in our case, it's primary human hepatocytes, right? Neonatal hepatocytes in this case. We know our cells don't recapitulate all the functions of neonatal hepatocytes. If you're looking carefully, I told you about how 3A7 metabolizes DHEAS, but the substrate we actually used in our experiments was DHEA. And there was a very good reason for that, because we tried DHEAS, we didn't see any metabolism. Now, we knew we had 3A7 there. We knew it was active, it metabolized midazolam, so we're just like, what the heck's going on? So we just decided to try the DHEA, then we saw metabolism. So we think that may be due to lack of transporter expression, so the DHEAS isn't getting in the cell. So it's these types of things that I think you have to be really careful. So for us, we're not there yet. I would not say we could put our iPSC cells right next to primary human hepatocytes and you're going to get the same IVE, unfortunately. So it's work in progress.
Thank you.
I don't know, Sarah, is there a way for us to find out if there's any questions online? Okay, good. Sounds good. Any other questions for today? Okay, otherwise I think we can go ahead and close our session. Please join me in thanking our panelists for their presentations and insights today.